Last time we study about the measure of variations, okay, and we done with the sample variance. So basically, just say it variance. It is a measure of variations, and this is the notation for the variance. We denote it by s squared, and this is the general formula of the variance. You have a sample consists of several values, x1, x2, x3, up to xn, something like that. Suppose that this is ages, for example. And then to get the variance, you have to compute the mean, the sample mean is denoted by x bar. And then you just subtract the x bar from those x. Okay? And then to get rid of negative value, you have to square them up. And at the end, you just do the averaging. And by averaging, just sum those values up, okay, from the first to the last. And due to something they call a problem, we will not divide it by n, but rather by n minus 1. So this process, we come up with a measure named x squared, and we call it the sample variance. And in the process, you square those values. Okay. So at the end, if you take back the square root of this measure, you will get what we call the sample standard deviation, a measure of spread, a measure of variation of a sample. Okay, so that's why we attach the word sample here. So it's called the sample standard deviation, and its notation is S. Okay, so this is one example of the standard deviation. So I hope you still remember this example about the group of 8 people. Okay, group of 8 people. And this is their is 10 years old. Second one is 12 years old. The last one is 24 years old. Okay, so our goal is to come up with a measure that informs us about their quality, on how much they are away from each other, right? Just simply the measure of spread or measure of variation. So to come up with that, you have to compute the mean. In this case, the mean is 16, okay, denoted by x bar. To get the mean, you get those values sum up and divided by the sample size 8 in this case. Then you subtract the mean from those values. Okay, 10 subtracted by 16, 12 subtracted by 16 again, 14 subtracted by 16, and lastly 24 subtracted by 16. And since mean is some value in the middle, when you subtract this way, some of you may be negative, right? But that's why we just square them to get it of negative sign, and then carry out the average. By average, we mean sum them up together and then divide it by roughly n. Of course, due to some technical reason, as I mentioned, we do not divide it by 8, but 8 minus 1. And then after summing up and do the averaging, we get 130/7 and take square root to get the standard deviation s, then you get 4.3 something. So this is called the standard deviation, and it is like the average deviation those guys away from 16. In average, they are 16, but not all of them are 16, right? Some are 6 years different from 16. Some are 4 years different from 16. Some even 8 years different from 16. So when you compute the standard deviation like this, you come up with the average of this deviation, okay, or the average scatter around the 16 the mean. So we would say that in average they are 4 years old away from the average. Okay? They are 4 years old different from the 16. So this is a measure. Just tell us how close they are from their center, in this case 16. And now I have 3 data sets. I have 3 data sets. Okay, group of, okay, let's say class A, class B, class C. So they have different ages. So can you see, look at the diagram, can you tell us about the difference, how much they are spread, okay, how much they spread from their center, or maybe you can say that they are spread among each other in general. So if you just like look at the 3 data sets, can you just look at how they arrange, how they distributed among each other? So which data set has the smallest spread? Can you look at those number? For example, group A, data A, we have 11, we have 12, we have 13, we have 216, we have 17, we have 18, we have 21, and this is how they spread. Okay, and the second group, the youngest is 14. Okay, 3 of them are 15, 3 of them are 16, and the oldest one is 17. And look at the third group that I see. So can you look at those diagram and conclude that which one has the smallest deviation in general by just observing? Data A, data B, or C? That is like the smallest spread. It just tend to closest compared to the other groups. Which group? A, B, or C? Hello? Okay, somebody can answer this. Silent. That's why I don't like online class because of this low interaction. Anybody here? I'm alone. So based on observation, do you think which group that tend to close together, and which group is kind of like
Group B, teacher.
Group B, right?
Yes.
Okay. Thank you. Okay. So which group that tend to stay away from their center?
Beta C.
That okay.
Beta C.
Okay, thank you. So if you look at the value on the right hand side, okay, those groups, those three groups have their center at 15.5. So this is the center. If you just observe where should be the center, it cannot be at 15. It cannot be at 16. It should be at 15.5, right? And the third group also at the same place. The first group maybe it's a little bit hard to observe, but based on calculation, we have the same center at 15.5. Then if you look at the way the data distribute around their center, in this case 15.5, the second group B, just tend to close, okay, close to 15 more than the other two, okay? And the data C just have the biggest spread, okay, away from their center. And look, the number just tell us that way. Okay? For example, the standard deviation of the group A just three something, right? And the standard deviation of the second one, which is less than 1, the smallest among the three, while the standard deviation of the third one is roughly 4.5, the highest one, right? So this last group has the biggest spread, okay, in terms of deviation, and the second one has the smallest spread. Okay, so if I just change this to 0, x equal to 0, anyone can tell me what happened to the original data set if the s is 0, exactly 0? I keep the mean the same, 15.5, and if we compute the standard deviation, we get 0. So what happened to the original data set? Okay, so as you can see, all the standard deviation are non-zero. Okay, they are all positive. But what if the standard deviation is 0? Okay, is 0, and I keep the mean the same, 15.5. So what should be the situation of the original data set? If you make the spread even closer to 0, okay, if the spreadness becomes 0, so what happened to those balls?
They're all on 15.
You mean 15.5?
Yes, they're all stacked on top of each other.
Yeah, they will stick to a single position at 15.5. Okay, so this is the situation that no spread at all. Okay, no spread at all, because all of them just fall in the same position, so no spread. Okay, so in real life, standard deviation just tell us about the quality. Okay, quality, how much they are different in as a group. Okay, so if everybody here in this class is as 18 years old, you have I mean very consistent. Okay, very consistent. I mean uniform. Okay, same quality. Okay, so no spread. Okay. But in real life, we never achieve zero standard deviation. Okay. So somebody may still remember about the difference between sample and population. A while ago, we just have you know, sample variance, sample, okay, sample variance, sample standard deviation. Mean the variance and the standard deviation belong to a sample. And now let me consider population. Okay, so if you change your data to a population, the measure gonna be called population variance and population standard deviation. And we're gonna use a slightly different notation. Okay, so look at the formula here and compare with that of I mean the variance of a sample. You compute the mean with it denoted by x bar, but here for the population the mean is denoted by mu, and then you subtract mu from those x and square them and then sum them up and then divided by, in this case, n. Okay, not n minus 1. And the notation for the population variance is not s square but sigma square. Okay, so just like any measure belong to the population, we use Greek notation, Greek letter. Okay, any measure belong to the sample, we use Latin. Okay, Latin letter. For example, s square. S is Latin, right? And now sigma. Sigma is actually the variant of the population. But we still use the same square, right? S square now switch to sigma square. And there should be a one-to-one corresponding between, you know, Latin and Greek letter. For example, everybody alpha correspond to A, right? Beta correspond to B. How about the third one? What is the name? The third letter in Greek. Okay, alpha, beta. What should be the third? So the third is gamma, right? Alpha, beta, gamma. How about the fourth? Delta. So can I ask you about sigma? Sigma correspond to which character in Latin? Sigma, this one. What should be the corresponding character of sigma in latent. S, yes, S. So we use the same letter, okay? But please keep in mind that any measure belongs to population, we always use Greek, okay? While that belongs to the sample, we use the Latin, okay? And when you take the square root of this guy, you will come up with population standard deviation. But this time, it is the measures of the population, everything. Okay? Population is everything, not just something. So this is the summary of those measures. So basically, mean, variance, and standard deviation are the most measures of a data set. You need mean to tell about how your performance for the first semester. You need mean to tell what is the income of our people as a country, okay? And standard deviation or variance just inform us about the consistency. Okay? Consistency means the quality, right? Yeah, quality. But in practice, you never assess to the population. What you assess is just like partial information, just sample. So if you want to estimate the mean, you have to compute the X bar, right? If you want to compute the sigma, you have to compute S to estimate its value, right? So in practice, the population parameter are all unknown that need to be estimated. All unknown, but you want to know. Okay? You want to know. And the way to estimate it is to use the same version. Okay? X bar gonna be used to estimate the new, and S gonna be used to estimate this sigma. Okay, okay, so I just close the mean and the standard deviation here, and don't forget this is the measure. Okay, this is the measure. Okay, so now we're gonna move to another measures, and this gonna be a test today. I will ask you to use this measure to summarize something for today. Okay? So we call quartile. Quartile. Okay, everyone. Quartile. Okay. Or in Khmer we just call it katil. Okay, katil. So quartile are a position that divides the whole data into 4 equal parts. Okay, you have 100%. You have 100% of data, and then you arrange them in ascending order from the smallest. Okay, from the smallest. So this would be the mean. Okay, the mean, the smallest one, and the highest gonna be on the right hand side, okay, the maximum. After arranging the data in ascending order like this, sometimes you need to find the position where I mean 25%, right? Just like divide everything into 4 pieces, into 4 equal parts. In other words, this should be a position called Q1, the first quartile, and this should be a position to call Q2, second quartile, and this should be a position called Q3, the third quartile, right? And once you divide in this case, there should be 25%, first 25% of the data on the left of Q1. And between Q1 and Q2, there are 25%. Between Q2 and Q3, there are another 25%. And the right side of Q3, there are the upper 25% of the data. Okay. So this is called the quartile. Okay. This is called the quartile. So can anyone tell me Q2 is something familiar? We already studied Q2 already, but in a different name. So what should be the name of Q2 that we have learned so far? Q2 is a position that divides the data into 2 equal parts. Okay. So it is
median.
Okay, that's great. Okay. It is the medians. Okay, a position that divides the data into 2 equal parts. But now we're gonna make it a little bit more detailed. Just not only divided by 2, just divide into 4. Maybe we have a different goal. Okay. So if you're trying to figure out the position of those two, this would be the formula. Okay. Okay. So Q2, it is in the n+1/2 position. This is not Q2. This is the its position. Like it is in n+1 divided by 2 rank value. Okay, it is in this position. For Q1, you just get n+1 divided by 4, and Q3, its position is in 3 times n+1 by 4. Okay, so this is the formula of the position. Okay, the position of those Q. So take a look at one example. Take a look at one example. So this is a sample consists of 2, 4, 6, 8, 9 values. So I want to compute those Q. Now let's focus on their position first. So since now the sample size is n, sample size is n. So the position of Q1, the position of Q1 is sample size +1 by 4, and then you get n+1 by 4. That will be 2.5 position. Okay, so this is the first, second, third. So 2.5 some value here in between the second and the third, right? So 2.5 is just like the position of Q1, not Q1 itself. So to get the value of the Q1, you have to find the average of the second and the third position, because Q1 is in 2.5 position, right? So the 2.5 position must be the average of the second and the third. So to get the average of the second and the third, you get their value, sum up, and divided by 2. Okay, so 12 plus 13 divided by 2, then you will get 12.5, right? 12.5 is the Q1. So similar calculation, you can get Q2, which fall in the fifth position. And the fifth position is easy to identify, 1, 2, 3, 4, 5. So this is Q2. This is Q2. Okay. And the variable Q1 is somewhere here. 12.13, 12.5. And the Q3 position, according to the formula, its position is 7.5. 7.5 again is between 7 and 8 position. So you're gonna take the average of these two positions. So you get 18 plus 21 divided by 2, and then you get 19.5. So this is Q3. Okay, Q3. So everybody, if you ask to interpret those Q, because any measure has its meaning. Okay, any measure has its meanings. So if I ask you to say, what is the meaning of Q2? So in this context, let's assume that these are age data of 9 people. Okay, after rearranging, the youngest is 11 years old, next one is 12, while the oldest is 22 years old. And now we found that the quartile, the second quartile, is 16. So what can you say about 16 as the second quartile, as Q2 in this context? This value are ages of a group of 9 people. So what would you say about 16, which is actually the Q2? What could you say about 16? What would you say? Anything can be said about 16. So my definition, 16 is the Q2, and Q2 is in the middle of the data set, right? So what would you say? Okay, I give you some clue. It is a value in the middle. So I would say that there are 50% of those guys, okay, who are younger than 16. Okay, 50% of them are younger than Q2, are younger than 16 years old. And if you say 50% of them are younger than 16, you can say something other way around. Okay? Other 50% older than 16, right? So now, can you say something about the Q1? Q1 is 12.5 years old. Okay, so make some reasoning. Can you say something about Q1? So what would you say about Q1? Just in terms of the way Q are constructed. Okay, look at the very first construction of Q1, Q2, and Q3, and based on their construction, you may draw conclusion accordingly. What can you say?
Teacher, quick question, Cha.
Okay.
But is it like we just divide the data into quarters? Is that it?
Yeah, but can you say in this context, just like now our Q1 is 12.5, and this data set are ages of 9 people. Now we get Q1 equal to 12.5 years old.
So I suppose we can say like a quarter of the people is around the age of 12.5 or under.
Yes, it would better to say under, not around.
Yes, sure.
Okay. Yes. So this is the way that you say about Q. Okay. Because sometimes you want to identify the position that containing, a quarter, as you said, okay, a quarter of the values, right? This is called the lower quarter, less than Q1. If you want it to be upper quarter, it should be more than Q3, right? Yes. Okay. And so what is the proportion of data between, so how much people there is who are between 12.5 to 19.5? How much portion of people who are between 12.5 to 19.5, or between Q1 to Q3? How much percent of proportion?
25%, Cha.
No, between Q1 to Q3.
75.
50.
50, yes.
Ah.
50. If you say 75, it should be more than Q1, right? Maybe one more than Q1, but less than Q3. Okay. So that would be the middle 50%. Okay, the middle 50% of the data. Okay. Hey. So to get the idea of the middle 50%, you may come up with a measure called the IQR. So IQR stands for interquartile range. Okay, interquartile range, which is the difference between Q3 and Q1. Okay, how far from the Q1 to Q3? Okay? So this is called the interquartile range. So you see the word range. So range is something that we learned last week. So what is the range? It's a measure of what? Measure of center or measure of spread? A measure of variation.
Measure of spread.
Measure of spread, right? So rank just tell us how much the data is spread, right, from the smallest to the largest. But this special range called IQR just intended to measure spread of the middle 50% of the data only, not the whole data, right? Because you want to ignore, you just ignore the first 25% and the other upper 25%. So if you ignore some value less than Q1 and some value less than greater than Q3, so in this case you just have only Q1 to Q3, and then in this case Q1 is the smallest and Q3 is the largest. And if you compute the rank in this case, it would be IQR, right? So IQR just give us a glimpse of spread, okay, in the middle, okay? Spread of the middle 50% of the data, right? Somehow it also just like a measure of variability, measure of spread or measure of variation. But I think compared to the ordinary range, IQR range may be stable because, sorry, I didn't touch that. Maybe it's a system error. Now, can you hear me?
Yes.
Okay. So last time, you see, this is a data set that's supposed to be the weight of several fishes, and some are 1 kilogram, some are 2 kilograms, and one of them is 5 kilograms, and we want to compute the rank to come up with how spread, okay, or how they spread, okay. So one of the measure is to compute the rank, which is the difference between the largest and the smallest. Then you get 4 kilogram difference. But if you look at the second data set, which is just like one value different from the above one, and the rank turns out to be so much different. Even in general, most fish are quite similar compared to the first group. But since this value is outlier, so strange from the rest, it makes rank so strange too. But from my perspective, I think the spread among the first and the second must be quite similar because majority of them are identical, right? So in this case, if you compute IQR, they will be same, okay? Because IQR, you will not take into account the 25% up and 25% down data. So if you ignore in that way, you will ignore also the outlier if it exists. And in this case, the middle percent of the data are gonna be same, right? That should be the reality, that the spread among these two group of fishes are somehow quite similar, right? So that's why when you know when you just use the IQR, it will become a better measure of spread compared to the ordinary rank. Okay. So I just use you know, those important measure we have. Okay, Q1, Q3, Q1, Q2, Q3, and also the X minimum, also the X maximum, to construct a special of graphical box plot. Okay, this is called box plot. Okay, box plot. Here is the name. Okay, box plot. We use box to plot, right? To plot the graph. So this is called the box plot from this data set that we have just computed, Q1, Q2, and Q3. So box plot, in box plot, you may need to emphasize the 5 summary measures: X minimum, Q1, Q2, Q3, and X maximum. So for example, a while ago, the X minimum is 11, okay? The X maximum is 22, Q1 is 12.5, Q2 is 16, and Q3 is 18.5. So you just put the scale of those number. Okay, dương đặt ai biết thử scale thôi ta lấy cái này ní đọc mùi hơi đọc pi cái này đọc pi lại ní đọc pi cái là okay. You have to put all of them in the right scale. Okay, put those 5 values in the right scale. Okay, so this is starting from 11. Okay, 12. It should be 12.5, right? Okay, 13. Okay, 13, 15, 16, 17, 18, 19, 19.5, let's say. Maybe the way I just constructed is not so accurate. Okay, this will be 20, okay, 21, and 22. Okay, so you just put those 5 measures along the scale, along the line, and then draw a box. Okay, draw a box starting from Q1 up to Q3, and then you divide the box by the Q2 to put at the right scale, right? And then please draw this as this maximum value and draw this as a minimum. And then you will come up with a box like this. We call box plot. Okay. So this is a box plot that somehow inform us about the information underlying the problem. Okay, and if you look at the rank, okay, I think I better just change this. Okay. So the distance between the starting of the box to the to the right, this is called the interquartile range, right? So you get 19.5 Q3 subtract by 12.5 Q1, and then you get 7. So you can say that the middle 50% of those guys are 7 year different. Okay? Yes. So this is some extent, right, of the spread, 50%. Okay, so this is called box plot, and what we're gonna use it for? Okay, what we're gonna use it for? So basically, plot or graph or charts just reveal us some information, right? So if you just want to use the box plot to describe the shape of the distribution of our data set, this is the way. If our data set is symmetric, okay? Symmetric means the mean and the median just fall into the same position, and the way the data just distribute just equal, okay, to the left and to the right. Okay? The way the data distribute on the left and on the right are roughly equal. Okay, so if you look at the histogram, the shape should be something like this. And if you just plot the box, this would be the box plot of a data set that is symmetric. Okay, so the box gonna be spread equally, as you can see here. So this is Q1, Q2, and Q3. So these two rooms gonna be the same, right? Same space. But if our data is not symmetric, for example, it is left skew. Left skew means the data gonna what? Spread out more on left, right? Again, left skew means the distribution of the data is more spread out on left. In other words, it more concentrate on the right. If it's more spread on left, mean it more concentrate on the right, right? So if our data set is left skew, this would be the shape of the box plot. Okay, look at the two rooms. This room is larger. This room is smaller. So anyone please tell me. So how much data set inside this room? How much proportion of data set inside this room? What is the percentage of data set inside this room? Okay. Please help me. Okay. This room just like what? Between Q1 and Q2, right? So how much data set? How much data set? This room.
Around 35%.
No. Please use the definition of Q1 and Q2. So how much data set fall between Q1 and Q2? Exactly. How much? Anybody, please? just refer back to the way we get Q1, Q2, and Q3, right? So my question is, how much data set fall in between Q1 and Q2? Because this position must be for Q1, right? And this position must be for Q2. So how much data set fall in between Q1 and Q2? It would be 25%, right? How about Q1 and Q3? Q1 and Q3, how much percent?
50.
It also 25%. So now, please tell me, there are 25% of people here in the first room, and also 25% in the second room. Which room is more concentrated? First or second? Yeah, this is the first room. This is second room. Which one is more concentrated? Which room? Same amount of student, 25%, 25%. Và tôi quay ná trên yên chieng của mẫu và đông chieng.
Second.
Second, okay. If the second is more concentrated, mean the first is less concentrated or has more spread, right? Has more spread. So that's why this is exactly the same as this shape, right? Sometimes you use a histogram to inform about the shape, whether it's symmetric or skew, right? And sometimes we can also use box plot to inform about the shape. Okay? About the shape. So this is the case when our data set is right school, mean the room on the right is larger, right? Room on the right is larger, mean more concentrate on the left. Okay. How about symmetric? How about symmetric? The room are equal, right? In terms of concentration. Okay. Okay, so this means that everybody can use, can use a box plot to tell about the distribution shape, okay, whether symmetric, skew, or right skew. So let's go back to our data set. Our data set is skew, left skew, symmetric, or right skew. Okay, this is the box plot from this data set. Okay, group of 9 students. So my question is, according to the box plot generated from this data set, can you conclude that our data set is symmetric, left skew, or right skew?
Symmetric.
Symmetric, yes, because the size of this room are quite similar. I would say that's the same, right? Because 12.5 to 16 and 16 to 9.5, just 2.5 different. Okay? The size of each room is 2.5. Oh, no, 3.5. Okay? 3.5. So same spreadness. Okay? Same spreadness. Okay. How about this one? if the box plot is in this way, it's symmetric, let's do a right square. Gonna be
Right screw.
right square, okay, because the room on the right is kind of like wider. Okay. Okay. So last point for today. So sometime we are curious if the data set containing string value that we name it outlier. Okay? So sometimes we want to identify if a data set containing outlier or not. So one way to identify outlier is to compute the z-score. Okay, is to compute the z-score, because z-score. So z-score is actually the standard value of those values. So for example, if you just want to test if a value is so strong compared to the group, you have to get that value subtracted by its mean and divided by its standard deviation, and then you will get its z-score. Okay? Because z-score is the standard diversion, okay, of that particular value. So if z-score just smaller than 3 and smaller than -3 and greater than 3, that value must be considered as outlier. So basically you may, right, okay, suppose that this is minimum, smallest, this is the smallest, this is the largest, okay, this is the largest. So suppose that center is somewhere here, the mean, the x bar, okay, the x bar, and suppose that one standard deviation is this. Okay, this is 1 sigma. This is 1 sigma. 1s, sorry, 1s. 1 standard deviation. So sometimes you want to know if a particular value is in how many if in how many standard deviation away from the center. So suppose the center is here. So if a value is three standard deviation from the center, this is 3s. This value here, this particular x. If this x is 3 units away from the center, it considered as far, right? Far means large in this case, right? Considered as so large compared to the general value. And it should be also considered as far on the left also. So if it's negative, I mean three steps on the left, it's also considered as far, right? So this is the criteria that we use to check if a number is so strong relative to general value. Okay, yes. So this is the formula to check. Okay, we call the z-score. So if the z-score is larger than 3 or or smaller than -3, it considered as so far or so strength, right? If it is more than 3, mean too large, right? Compared to the rest. If its z-score is less than -3, too small compared to the rest. Okay, so for example, you get SAT test, a math test. Okay, I think maybe this is an IQ test, right? SAT test, and then you get 490. Okay? I'm sorry. A lot of people join SAT test, an IQ test, right? And a lot of people take the exam, the SAT test, and then on average they get 490. Okay? The average score is 490, and they have a standard deviation of 100 score, right? So now somebody get 620. Do you think that this is considered as too high compared to the majority or the general student, the general score? On average, student gets 490 and have deviation of 100, and a student now get one particular student gets 620. Do you think that 620 is considered as too high compared to the average, or not yet? In this case, you have to compute the z-score of 620. Okay, so convert 620 to its z-score by subtracting by the mean and divided by this x, the standard deviation. And then in this case, you get 1.3. And 1.3 is in this rank. It's not so far, right, from the center. So this means that somebody who gets 620 in SAT's exam are not considered as too high yet. Okay, just because it's just like 1.3 step away from the center, right? So if I say somebody get, if I say somebody get 800 score, what can you say? 800. Somebody get 800. It considered as too high compared to most of the student or the general student. A student get 800 score. So what is your idea, everyone?
Too high.
Too high, because in this case, the z-score is, what is the z-score?
3.1.
3.1. Yes. So how about just figure out a number for me that is considered as too low compared to general student? Too low. What would be the score? What would be the test exam score? Too low. Just give one example. Quick example. It's too low.
108.
108.
80.
Oh, 180. Okay? 180. So So what is the z-score for this value?
Minus 3.1.
Okay, yes, that's great. Okay, so now we have a clear criteria of saying if a number is too large or too small compared to the group. Okay, we use a z-score criteria. So this is the one that we use. Okay, okay, so this is called the z-score. And so let's sum up what we have learned today. We have done with quartiles Q1, Q2, and Q3, a measure of locations, okay, 25%. Sometimes it's so useful when it's come to find the quartiles to get a quarter of something, right? We're interested in 1/4 or the last quarter or something like that. And secondly, we have used those values to construct a special plot called the box plot. Okay, and lastly, we have used the z-score to identify outlier. Okay. Okay. So now I have one problem for you. So please look at this. So please refer to your course reader on section, okay, problem 3.17 in section 3.2, measure of variation. Maybe the page is a little bit different from your course reader. Because I just use the old version or original textbook. I'm sorry, I would have make it consistent. Sorry. So just trying to check for this instead rather than look at the page, right? So 2.3, measure variation in shape. And please go to problem 3.17. Okay, 3.17. So this is I mean the balance scale that named after its developer, Catherine Birch. This scale is very popular in clinical tests of a person's static and dynamics balance ability. Okay, so SAT just measure IQ, right? IQ ability. The Birch balance scale, or BBS, is just like a measure of balance ability. Yeah, balance ability of a person. I don't know. Maybe you just go around in a circle and then how much you can control your balance. Okay? So the score just have a scale from 0 to 56. Okay. Higher value mean better score. So the cutoff score is 45%, mean that the score less than 45 indicate greater risk of falling. So if you have score less than 45 in BBS, your stability is not good, you have a greater risk of falling. So this file containing score, BBS score of 20 older patient at the hospital. So please try to answer these questions. Okay? Try to answer this question. So this is your task for the remaining part, because I don't want to spend much time on lecture because it's online, right? Maybe 1 hour, a little bit is okay. So more than that gonna make you frustrated, okay? with the lecture. So now I just finish the lecture here and just give you one thing. Okay. So trying to answer this and submit by today. And then you are free. Okay. So look at the questions. Compute the mean, the median, compute the variance, standard deviation, rank. If some value that not considered in the lecture, please skip it. For example, coefficient of variation, you can skip it. So z-score you have to compute because we already consider a variable. And please explain each value. Okay. And C just say about the schoolness. Are they school or not? If this, how, right? And I recommend you to, after you compute this measure, please somehow plot the box plot so that you can answer the schoolness easily. Okay. And then read the D. Okay, read the D carefully and trying to come up with conclusion. So this is the task for you. So can you find this problem in your textbook, in your course reader? 3.17. You may use R to compute the mean, the median, the variance, standard deviation, or even rank, or even z-score. Just make it. But trying to answer it point by point, right? So the last question is very important. Okay. So please try to answer this in a meaningful way, okay, based on the knowledge that we have learned so far. Okay, so this is your task, and you can submit it. Okay, I give you more time because I don't want to make everybody rush. Okay, I give you until 12 midnight. You okay with this? Hello?
Yes, teacher.
Okay. So try to make it meaningful, because this is gonna be important for you when it's come to data interpretation. Okay. So now you have data like this. Yes. And don't forget one additional thing: create box plot, so that you can answer question C by looking at the box plot. Okay. Yes.
ពួកខ្ញុំត្រូវ submit all code ដែរមែនក៏អត់ទេ
I need only the PDF version. Okay.
Okay.
Please use R code as a computational tool, but when you get, for example, get the value, just put it, just type it in a file. Okay.
Okay, sure.
Yeah. And then if you have to generate the plots, bring the plot to your Microsoft Word file, right? And then save it as PDF.
Okay, sure.
Okay. So don't forget to submit it. This is kind of like a small report especially question B. The way you're trying to answer question by question, just make you to understand the way to get useful information from this raw data set. Okay, so kind of like a small report to make sure that what you submit just meaningful, right, in terms of interpretation.